In this example here, we're going to look at how capacitive elements are used to to measure changes in capacitance. And this circuit is analogous to, with a resistive circuit, a voltage divider circuit. So this circuit that we see right here is also a voltage divider circuit, but it's a capacitive voltage divider circuit. And this is a common circuit in a lot of modern touchscreen device applications. So your iPhones, ATM screens, things like that use clear capacitive elements, and when you touch your finger to them, it changes the capacitance in one of the legs of this voltage divider. And we're going to develop an equation, or develop the relationship between the input voltage and the output voltage, and see how this can be used to monitor for touchscreen types of interfaces. The important thing to note here is that, as we've learned in class, capacitors don't change or don't allow any current to flow through them when they're operated in the steady state. So if we had a constant supply here, if we had a constant 5-volt voltage supply, this output voltage would never change. And that's something that is not going to be very beneficial for electronics if we're trying to monitor for a touch change or something like that. So where this voltage divider circuit comes in handy is when we have a time-varying input signal and we want to reduce the output to some smaller voltage value for that time-varying signal, like a sine wave input. So our input may look like a large sine wave, and our output, what we're going to find, is going to be some smaller amplitude sine wave output that's going to be scaled somehow related to these capacitance values. So just like a resistive circuit, if we were going to try to determine the output voltage across this capacitive element, what we would do is we would start with a current balance. We would look at this node right here, and we're going to call the voltage there, let's call this V out, well, because it's given there. And we're going to look at the current that passes through these two paths, one going through capacitor 1, one going through capacitor 2. All right, so we're going to perform Kirchhoff's current law balance, and Kirchhoff's current law is going to tell us that the current that passes through capacitor 1 plus the current through capacitor 2 must always sum to 0. And what I'm going to do now is use my current to voltage relationship for a capacitive element, which says that the current through a capacitive element is going to be proportional to the capacitance times the rate of change of the voltage, or the potential, across that capacitive element. All right, so for capacitor 1, it's going to be the capacitance of capacitor 1 multiplied by the time derivative of the potential across capacitor 1. Okay, just like with the resistive node voltage analysis, we're going to assume that the highest potential exists at the node that we're doing the analysis for. So here the potential is V out, and the potential that it's going towards, or that the current would be leaving towards, will be this input potential right here, which we're calling V1. And remember that these are going to be functions of time, so when we take the derivative, we'll wind up with the derivative of these functions of time. The current passing through capacitor 2, substituting in our current voltage relationship, will be C2 times the rate of change, or the derivative of V out, minus our 0 voltage reference point here, or ground. So V out minus 0 has to sum to 0. So now, taking the derivative of everything here, I wind up with C1 d dt, dV out dt minus C1 dV in, or dV1 dt, plus C2 dV out dt is equal to 0. Doing some rearranging, I can get my input voltage and my output voltage derivative terms all on different sides of the equation. And doing a little bit of algebra, I can wind up with an expression that says the output voltage, or excuse me, the dV out dt is going to be equal to the capacitor 1 value divided by the sum of the two capacitances multiplied by the rate of change of the input voltage with respect to time. Okay. After I do that algebra, I recognize that this is a fully separable differential equation. All I have to do to come up with the solution for this is to integrate both of these with respect to time. So if I integrate from time 1 to time some other arbitrary time, time 2, dV out dt with respect to time, and then I pull my constants, my constant capacitance values out, and integrate again from t1 to some other arbitrary time t2 of the input value. Right, to be mathematically correct, what I wind up with here is I wind up with these derivative terms don't really cancel each other out. It just changes what I'm integrating over. So really I'm going to be integrating from the output voltage at time 1 to time 2. Oops. All that is then going to be equal to C1 over C1 plus C2 times the integral from Vn, or V1, at time 1 to V1 at time 2 dV. Right, and then finally, solving all of this, what I wind up with, the integral of dV out will just be V out. Then I'm going to evaluate it at these two limits. So that will give me the output voltage at time 2 minus the output voltage at time 1 is going to be equal to C1 over C1 plus C2 times the input voltage at time 2 minus the input voltage at time 1. Okay. So what this tells us is that the output voltage is just going to be a scaled value of the input voltage at a given time. Most of the time, the application that we're going to be looking for is we're going to somehow try to make this output voltage at time 1 equal to 0. So we would like these terms to go away, and then if they're both 0 at some initial time, if we always reference that time, when the output voltage and the input voltage are 0 initially, as long as that's the case, then our output voltage is just going to be this scaled value of the input voltage. So that means that if I put a sine wave of a large amplitude in, I can divide that down and make it a smaller amplitude sine wave at the output voltage right here. And that's exactly what happens when you use touchscreen devices. In touchscreen devices, C1 and C2 are a fixed value, and then when you touch the screen, your body actually acts as a capacitor, which adds another capacitor in parallel with this C2, with either C1 or C2, which is going to change that value, which is going to change the scaling, and thus going to change the amplitude of the output voltage. So looking at the amplitude of the output voltage, looking for a change in that, tells us that the user has touched the screen. And you can then, if you have a bunch of these types of sensors on the surface, you can determine where the user had touched the screen as well.